Welcome to Homework Lib.
Hi, so for this question, first of all, we want to make a buffer with a pH equal to 1.15. How do I choose the species that I'm going to employ for that buffer? What I'm going to do is to calculate the pKa. What is going to be the best choice is for which the pKa is closer to the desired pH. Remember that for this pH, the ideal pKa would be equal to 1.15. That means that the Ka for the acid should be 10 to the minus 1.15. By looking at the table, there are only two possible options that are going to be able to somewhat get close to it. And the two options that we're going to have are iodic acid, so HiO3, which has a Ka of 1.7 times 10 to the minus 1. And the other one that gets somewhat close, but spoiler alert, it is not going to be a good choice, has a Ka for oxalic acid of 5.9 times 10 to the minus 2. If we calculate the pKa for each of these guys, the result is, in this case, 0.77, and for the other, 1.23. Oh, so guess what? Actually, the one that fits best our description is oxalic acid, because the difference of the pKa minus the pH, course in absolute value, is the lowest of all of the acid. In this case, it's going to be 1.23 minus 1.15, so zero point 0.08. And you can see clearly that for iodic acid, that value is larger. So the correct choice would be employing oxalic acid as a buffer for our solution. Question 2 to ask us for the chosen acid, what is the pKa? The pKa is this, 1.23. And next we're going to have, so for question 2, pKa equals 1.23. And for question 3, we asked to make a dilution in order to get a specific concentration. So we want to make 325 milliliters of a solution that is 0.223 molar on the acid that we chose in part A. But we only have 1.6 molar solution. So we know that the final volume would be 325 milliliters. The final concentration is 0.223 molar. And the initial concentration, it is going to be 1.6 molar. So we can use C initial, volume initial is equal to C final, volume final. Thus, the initial volume required would be final concentration times the final volume divided by the initial concentration. So we get 325 milliliters. We can leave it directly in milliliters. That is going to be our final result units. We get 0.223 molar divided by 1.6 molar. The result for my initial volume required is going to be, rounding up, 45.3 milliliters. This is actually 45.297, but we can round it up to 45.3. And finally, in part 4, what is the pH of the solution made in question 3? Of course, this is not going to be a buffer, but a solution that is 0.223 molar of oxalic acid. 4. So in order to know the pH, let's remember how this behaves when it gets into contact with water. Oxalic acid plus water is going to produce, it is going to produce HC2O4 minus plus H3O plus. This is going to be my initial concentration. So we can go ahead with our ice table. I'm going to abbreviate this number with C0. Recall, this is going to be equal to C0. We begin with 0, 0, 0. Well, water, it doesn't matter. It's a pure substance and it doesn't enter into the equilibrium equation. And amount X, it is going to dissociate in water. So we get at equilibrium C0 minus X, X, and X. That means that our Ka for this acid, just a reminder, concentration of HC2O4 minus times concentration of H3O plus divided by concentration of H2C2O4. This value for Ka is equal to, from our table, 5.9 times 10 to the minus 2. And this will be equal to x squared divided by C0 minus x. Remember, x times x from this section and C0 minus x. Now, in this case, our value for Ka, it is not small enough to make the approximation that C0 minus x is going to be equal to C0. So, for this scenario, we're going to solve the full equation. Just for sake of simplicity, I'm going to use Ka instead of the number, just to make it less confusing. So the quadratic expression that comes from this becomes x squared is equal to Ka times C0 minus x, which is KaC0 minus Kax. Thus, x squared plus Ka times x minus KaC0 needs to be equal to 0. Replacing the values, x squared plus 5.9 times 10 to the minus 2 times x minus the result of the product of Ka with C0, which numerically is going to be 0.013157, needs to be equal to 0. Solving for this equation, we find the two different values for x, x1 and x2, equal. We get a negative value that is minus 0.14794, and the positive result that is 0.0889, 889.4. Okay, so what is the correct result for us? Of course, it is going to be x2, because it is positive and we cannot have negative concentrations. Now remember, x is the concentration of H3O plus that I'm going to have at equilibrium. So this is equal to concentration of H3O plus. So we can add up the label molar over here. That means that our pH will be equal to 0 logarithm of 0.08894, which is a pH of 1.051. And that will be all. Thank you very much.